Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irfan bin Muhammad Riaz, and now I will be presenting on my final year project, which is the finite element modeling of ultrasonic assisted milling of borosilicate glass. My supervisor is Sir Muhammad FAUZI bin OTHMAN, and my co-supervisor is Professor MADYA Dr. JURI SAEDON. This is the content for this presentation, which includes the project summary, problem statement, objectives, project scope and limitations, literature review, methodology, data collection and finite element modeling, results and discussion, and lastly conclusion. Move on to the first part of this presentation, which is the project summary. Machining of brittle materials is common in the manufacturing industry, but few modeling techniques are available to predict materials behavior in response to the cutting tool. Ultrasonic assisted milling has an outstanding performance in machining hard and brittle materials such as glass. This is a very useful process where machining of hard and brittle material becomes very difficult, or in some cases, it is impossible to machine these materials by conventional methods. In this study, the ultrasonic milling process on the borosilicate glass will be investigated by using finite element modeling to understand the effects of ultrasonic assisted milling in the machining process. Move on to the next part of this presentation, which is the problem statement. In most industries, machining of brittle materials is becoming common and frequent. Unlike ductile material cutting, which is dominated by shear deformation across the shear plane, brittle material cutting is driven by fractures. The high cutting temperature in machining processes of brittle materials is another problematic issue and places negative influences on machining performances. Thus, a finite element model on the ultrasonic milling of borosilicate glass is developed and studied in this project to analyze the effects and potentially overcome the problems. Move on to the objective of this project. The first objective is to model an ultrasonic assisted milling process for borosilicate glass using finite element modeling, which is done by using the Abacus software. The next objective is to investigate the effects of ultrasonic assisted milling process on borosilicate glass, which mainly focus on whether the borosilicate glass is damaged or cracked during the cutting process. The last objective is to validate the ultrasonic assisted milling model with the results of a journal article. Move on to the project scope and limitation. The scope of this study is focused on creating a suitable finite element model that can undergo the machining process where the tool is able to cut the workpiece as intended. The workpiece with the properties of borosilicate glass is used in the finite element modeling. Some limitations and considerations need to be focused on for the finite element modeling to be successful, such as the type of material, the design or shape of the tool, the input parameter used in the finite element model simulation, and the response parameters such as the cutting rate, the force, and the chip formation. Move on to the literature review. The first literature review is on the finite element modeling. Finite element modeling is the simulating process to determine the response parameter of the machining process, such as the cutting force and chip formation, so that it can be assessed using the finite element method. Finite element modeling consists of two components, which are pre-processing and post-processing. Mesh size and order is crucial to create a balance between accuracy results and runtime. In pre-processing, the main focuses are to assign the type of element, insert material properties, use appropriate mesh elements, and apply boundary conditions in the form of load and structure. In post-processing, the main focus is to generate the desired output or results, such as the cutting force, accurately. The next literature review is on the failure criteria and cutting force. Machining of titanium alloy was investigated by 2D finite element analysis performed to understand the effects of ultrasonic machining. Workpiece material of titanium alloy was modeled as plastic, and to observe the effect of failure criteria, conventional turning simulations were run with and without failure criteria. Serrated chip formation is obtained in simulations with failure criteria, while chip shape is smooth in simulations without failure criteria. Maximum temperature in ultrasonic assisted turning operations is higher by compared with conventional turning operations. The motion of the tool retractions in ultrasonic assisted turning allows some duration to cool down for the tool cutting edge. Cutting force is reduced in ultrasonic assisted turning operations compared to conventional turning operations. This is the cutting force for conventional turning and ultrasonic assisted turning for the titanium alloy, which is done in the previous literature review. Move on to the methodology of this project. The first step is to do research and data collection. In this step, all the machining parameters and properties of the workpiece and tool is being researched and collected. Then, the testing finite element model in Abacus takes place. This step is done by referring to journal articles, researchers, and also the internet. Next, we move on to create the finite element model, where all the data from the research and data collection step is used in this step to create the finite element model and run the simulation and to see the cutting process. If this step is successful, then we move on to the last step, which is analyzing the data. And if this step is not successful, then it is required to start the step from the beginning. The last step is analyzing the data, where all the data is being analyzed and compared with other data from researchers and the internet. Move on to the data collection. The material that were used for the workpiece and tool is borosilicate glass and tungsten carbide respectively. The properties of the workpiece and tool were defined by density, Young's modulus, and Poisson ratio. Damage criteria were also added to the properties of the workpiece and tool where Johnson-Cook damage criteria were used. The data was collected from studies and experiments done through journal researchers. The first table shows the property of borosilicate glass, and the second table shows the properties of the tungsten carbide, which is the tool that is used for this cutting process in the finite element model. This is the stress strain properties for the tungsten carbide, which is the tool. As you can see, as the effective plane strain increases, the yield stress also increases. This property is referred to the researchers and internet. The Johnson-Cook data failure model was added into the finite element model to account for a chip separation process. This allowed the cutting tool to move freely without causing substantial mass distortion near the tool tip. The first table shows the Johnson-Cook material model for borosilicate glass. A, B, M, C, and N are constant for the Johnson-Cook material model of borosilicate glass, and it is taken and obtained from experiments done by other researchers. The second table is the Johnson-Cook damage parameters for borosilicate glass, and the third table is Johnson-Cook damage parameters for the tungsten carbide. The value of D1, D2, D3, D4, and D5 were also obtained through researchers and also internet. D1 is the initial failure strain, D2 is the exponential factor, D3 is the triaxiality factor, D4 is the strain rate factor, and D5 is the temperature factor. Next, we move on to the finite element modeling. Abacus explicit software was used in this study for the finite element modeling process. As you can see in the picture shown, that is the finite element model that was done using the Abacus software for this project. The table shows the finite element model parameters that were done and used in this project, where the workpiece has a length of 5 mm and has a width of 4 mm, and the velocity of the cutting tool is 90 m per minute, and the depth of cut is 0.1 mm. As for the mesh, the workpiece is divided into 3 parts. The top part, where the cutting process takes place, has an element size of 0.0005, the middle part has an element size of 0.001, and the bottom part has an element size of 0.00025. The total number of mesh elements generated on the workpiece is 2318. As you can see in the picture shown, which is the mesh that was done using the Abacus software for this project. The mesh for the tool is set as dependent with the workpiece. Next, we move on to the results and discussion. The first result that was achieved is the tool is able to undergo the cutting process on the borosilicate glass without causing any damage. Reduction in simulation time was achieved by reducing excessive distortion in the chip separation region by specifying a very low damage evolution threshold, which allowed the distorted element to be deleted quickly. The picture shows the cutting process that was done using the finite element model in the Abacus software. Chip creation must be accompanied by fracture criteria that may be used to determine when the material is separated from the workpiece, resulting in the production of chips. The figure below shows the finite element model simulation of the cutting process with damage criteria, which is Johnson-Cook damage criteria defined on the workpiece. This shows that the results of the cutting simulation are more accurate as it resembles the actual cutting process and could predict the actual material behavior during the cutting process in real life or experiments. Therefore, damage criteria are an essential feature to be defined in material properties for finite element modeling and simulation. The next result that was achieved is the tool is able to demonstrate an ultrasonic vibration cutting process on the workpiece as well as generate the force that shows the motion of ultrasonic vibration. According to the simulation, the material is intermittently removed in the ultrasonic assisted milling process. Over the course of a whole vibration cycle with the time period T, it only engaged at the period corresponding to the workpiece cutting portion. As a result, the force diminishes throughout the course of a vibration cycle. The force generated during the machining process used in the ultrasonic assisted milling method is far less than that used in the traditional machining. This is because the tool does not come into direct contact with the substrate during the ultrasonic assisted milling process, which is meant by the tool vibrates during the cutting process. As you can see, this picture shows the force that was generated during the cutting process in the finite element model that was done in the Abacus software. The force indicates the motion of ultrasonic vibration of the cutting tool during the cutting process. This is the video taken during the cutting process that was done in the Abacus software for this project. As you can see, after the cutting process, the tool moved downwards and back to its original position to indicate the ultrasonic vibration during the cutting process. Next, we move on to the conclusion. Finite element modeling simulation is also an effective method in order to predict material behavior during the cutting process as well as ensure the suitable parameters and properties needed in order to carry out the machining process in real life or experimentally. Modeling with finite element programs enable the production of partition lines inside the model, which were used in this study to improve the accuracy of the results. The definition of damage criteria in finite element modeling simulations is also essential in order to predict and obtain accurate results. Force during the machining process is much less and more effective when using ultrasonic machining for brittle materials to avoid fracture or cracking in workpiece. Next, we move on to the reference. Some of the references that were used in this project. That's all from me. Thank you and Assalamualaikum warahmatullahi wabarakatuh.